Well, I'd like to thank to the organizers for the opportunity to talk here, and my talk is about on the braid group action on exceptional sequence for the weighted projective line. This is a joint work with Hagen Meltzer and Eduardo Marcos. In this talk, we consider K is an algebraically closed field, and for a weighted sequence P, P1, Pt, we call a weighted sequence P, where P1, Pt is integers bigger or equal than 2, and also LP is the abelian group with the generators x1, xt, and with the relations p1 x1 equal to pt xt equal c. And this is LP is an ordered group, and we consider further a sequence of parameters lambda. This sequence is lambda 3, lambda t, where lambda I is different 0, and lambda I are non-zero and pairwise distinct elements of K. Well, in this talk, S denote the algebra, this quotient by the ideal xi pi plus x1 p1 plus xi x2 p2, and this then we can see here that this depends of the parameters and also the weight sequence. Well, X is the weight to the projective line, and the weight to the projective line is defined to be the LP, the LP projective, the LP grade, the projective scheme of SP lambda. And for us, we consider here the category of coherent sheaves on the way to the projective line. This category is an abelian category and is also a hereditary category. This means that the xi of AB is 0 for all AB in the category of coherent sheaves. And xi is 0 for all I here is for all I bigger or equal than 2. Then, and also this category has the property that the home and the x are has finite dimension. And well, this category of coherent sheaves has the property is a category that has series duality, and the series duality is of the form x1 AB is isomorphic to the dual of the home A. Here is W, where W is the dualizing element of the LP group. Well, for us in this disposition, it's important to note that when we have a series duality, then one consequence is that this category of coherent sheaves has Auslander-Heiten sequence. And note that we denote here in this talk we denote by O the structure shift on X. And for each object in the LP group for each X, we can associate a line bundle in the category of current shifts. And this is a bisection. We have an isomorphism of group here. And the set of morphism between two line bundles, we can say that the home of OX, OI is the degree of the algebra S in the degree Y minus X. And I like to talk about the action of the braid group on a kind of a sequence that we call exceptional sequence. Then the first thing that I need to define is what means an exceptional object in the K category H, where H here is a hereditary category. Then one object E in this category is an exceptional object if the endomorphism ring is K and if the X1 is 0. Then this is the definition of exceptional object. And the definition of exceptional sequence the definition of exceptional sequence in this category of current shifts is the following. We call epsilon here is an exceptional sequence if this sequence is a sequence of exceptional objects in the category of current shifts. And also we have this object satisfies this condition. The homomorphism between EJ, EI is 0, and the X between EJ, EI is 0 for all J bigger than I. Then this is the definition of exceptional sequence. And when R is 2, we call this kind of sequence exceptional pair. And here, in general, in this disposition, for us, the number of guys in the number of guys in the exceptional sequence is the rank of the Grothendieck group. And in general, this kind of exceptional sequence we call this a full exceptional sequence. Full exceptional sequence. Exceptional sequence. Then, in the case that R is the rank of the Grothendieck group, we call this full exceptional sequence. Before to talk the next definition, it's important to say that some studies about exceptional sequence give us an interesting description of the derived category of sheaves for some specific variety. But here we study exceptional sequence in order to give a new and intrinsic proof of the transitivity of the braid group action on the set of a full exceptional sequence for a weighted projective line. And this new proof, this intrinsic proof, in this new intrinsic proof, we do not use the corresponding result of Crowley-Bulver for modulus over hereditary algebra. And there was an application of this. We prove also that the strong global dimension of the category of current sheaves on weighted projective line does not depend of the parameters. And if it's possible, I will say also another application too. Then the next definition is the definition of the braid group. This is the definition that use the relation. We call sigma 1, sigma r the elements of the braid group BR, and these elements satisfy this condition here, this equality for I minus j bigger than 2, and this other equality here, sigma I plus 1, sigma I plus 1 is equal to sigma I plus 1, sigma I. This is the definition of the braid group. And now I'd like to give the definition of mutation of exceptional sequence. This was defined the first time by Rudakov and Gorodentsev. And here we have an important thing to note. If we consider a pair of an exceptional pair, A, B, in the category of current sheaves of X, then it's possible to prove that the Hom or the X is 0. And because of this, for example, if in the first case that in the case that the Hom is different 0, then it's possible to define this morphism here, the canonical morphism, and this canonical morphism is possible to prove that it's surjective or injective, but not bijective. And well, with this morphism, if Hom is different 0, then we can define the left mutation that associates to an exceptional pair. We can associate another exceptional pair, LABB. Well, and now we have, with this morphism, we can define 3 kinds of exact sequence. The first one is this one here, is the kernel of the canonical, morphism here. If the canonical morphism is surjective, then LAB is the kernel of this morphism. Then we can associate AB to this pair here, where the kernel is the kernel, where the LAB is the kernel of the canonical morphism. In the case that the canonical morphism is injective, then we take the co-kernel of the canonical morphism to define LAB. And in the case that the Hom is 0, the Hom of AB is 0, and the X is different 0, then we consider the universal extension. Okay, and the universal extension is here. Well, with these 3 kinds of exact sequence, we have another thing to say. In the case that the Hom is 0, then we can we associate in the case that the Hom and the X is 0, we associate the pair AB to the pair BA, and in this case, this is B is LAB. Then we associate the exceptional pair to this other exceptional pair. And now the definition of the action of the braid group is the following. If we take a guy here in the braid group, then the action of this guy here in an exceptional sequence here is the following. We take here we have the same guys, and here we do a mutation of this guy, and we put here the mutation. The other ones are the same. And this is the action of the braid group on a full exceptional sequence. And if we take another kind of the co-canonical morphism, then we can define the right mutation, and also we can define the action of the sigma I minus 1. Well, with this in mind, with this kind of action, we have proved the following in this joint work. The action of the braid group BR on the set of full exceptional sequence is the category of a full exceptional sequence in the category of coercitive is transitive. Well, I don't have time to say about the idea of the proof, and now I'd like to talk another thing. Here is the following about the strong global dimension. The strong global dimension for a weight to the projective line is defined. We define it in the following way. We have the strong global dimension is 2 if all tilting complex of the derived category is of the form for a fixed J. Otherwise, we define the strong global dimension is the maximal number m plus 2 such that there exists a tilting complex T in the derived category of the category of current shifts such that the tilting complex is of the form here from 0 to m with Ti in the category of current shifts and also with T0 non-zero and Tm non-zero. Well, we have proved with this definition in mind that if we take two projective lines, x and x prime, and here is the same weight sequence that here, and different kinds of parameters, then we have proved that the strong global dimension is the same. Then is important to note here that we take the same weight sequence, but different kind of parameters, and we have proved that the strong global dimension is the same. Well, another thing that we have proved is that if we take now is one definition. If we take F1, Fr are homomorphism of group between the Grothendieck group 2Z, and here R is the rank of the Grothendieck group, and the epsilon is a full exceptional sequence. We can define a matrix, R by R matrix M epsilon, that depends of the exceptional sequence in each position of the matrix Ij. We put this element of Z, Fij. Then we have proved that there exists a constant C such that the determinant of this matrix is C or minus C for all full exceptional sequence epsilon in the category of current shift. And this is the last result, and thank you very much to this opportunity.